Bismillahirrahmanirrahim. Symmetry reductions of differential equations. In this video we are going to reduce PDEs into ODEs using Lie symmetry method. So reduction of PDE to ODE by symmetry method. We will use a generator and find invariants of the generator, use them to reduce the PDE into ODEs. In fact, they are Lie symmetries, so we use Lie symmetries to reduce PDEs into ODEs. This technique is widely used in mathematical physics and applied mathematics. Differential equation that admit symmetry transformation reduce to from PDE to ODEs. So those differential equation which admit Lie symmetries can be reduced from PDEs to ODEs. Special case is the similarity transformation. If a PDE admit scaling symmetry, that scaling symmetry give us similarity transformation which reduce the PDE system to ODE system. Symmetry transformation generate invariant variables, and those invariant variables are used to reduce the PDEs to ODEs, or in some cases it solves the given partial differential equations. What these variables do, they simplify the equation. They simplify the equation, or they convert a PDE into ODE. Lie symmetry generator. The Lie symmetry generator is defined in this form, which is given over here. This is for the okay, this is the Lie symmetry generator. So here we have a different PDE into UTX, where U is the dependent variable, T is the independent variable, and X is also the independent variable, but this is time variable and this X is space variable. This is the corresponding generator. What this generator do, it give us invariant transformation. Okay, invariant surface. What is invariant surface condition? Let's derive this. We have a surface U is equal to UTX, and we can write it as F of T, X and U, which is equal to U minus T minus U. This is U, T and X. Okay, so is equal to 0. So this is the surface. This is the implicit form of the surface. Now we have generator xi partial by partial t plus tau partial by partial x and plus eta partial by partial u. Okay, operate on this surface F, which is a function of t, x and u. Okay, and this is equal to 0. The surface is invariant under this generator. So what it do, xi ft plus tau fx plus eta fu, derivative with respect to equal to 0. Now what is ft? That is derivative of this this function with respect to t. So let me write it over here. ft is equal to minus ut, fx is equal to minus ux, and fu is equal to 1. If I differentiate this with respect to t, I will get partially, so I will get ut, minus ut. With respect to x, that is minus ux, and with respect to u partially, that is 1. Putting these value in this equation, let's say this is 1. So then 1 implies xi ft, that is minus ut, plus tau fx is minus ux, and plus eta fu, that is 1, and this is 0. So simplifying this equation, we get xi ut plus tau ux is equal to eta, which is given over here. So this is called invariant surface condition. Solution that satisfy these conditions are invariant solutions. So this is invariant surface condition, and this is the corresponding derivation of the invariant surface condition. So we search out u, which is solution of the given PDE, and use the generator xi, tau and eta. Here if it satisfy this equation, that will be invariant solutions. Okay, characteristic system. This is the characteristic system. You see, we have the invariant surface, which is xi. Oh, let me write over here. Xi ut tau ux is equal to eta. So the characteristic equation for this first order PDE take the form dt xi dx tau and du eta. So this is the characteristic system of equations. Solving these equations, we can find similarity variable if the generator is scaling. Okay, so similarity variable corresponding to the particular generator, which is called scaling symmetry. So for all cases we solve this. If it is not scaling, then it will be invariant solution, and if it is scaling symmetry, in that case we will be interested in similarity solution. We discuss in detail these two type of solution and compare them in one videos, which is on the comparison of similarity and invariant solutions. So the detail of the similarity and invariant solution are given in that video. Okay, so this is the characteristic equation, and this is the basic and the fundamental equation of symmetry method, which are used to determine the transformation which will simplify the given PDE or ODE system. Okay, example 1. So we take the heat equation, and the detailed calculation is I mentioned given in the previous video, but this is the least symmetry generator of this differential equation. This is the solution of the characteristic equation for this generator. Taking uxt as f of eta, we can convert this differential equation into ODE, and the detailed calculation will be given in the previous video, but I'm not interested to go further in that. You have to search out for the similarity and invariant solution video. The calculation of this this eta as well as the this ODE, which we discuss in that videos. So this is the reduced form of the heat equation. You see, this is now an ODE. In fact, the f double dash depend on eta, and eta by 2 f dash, which depend on etas, equal to 0. So this is ODE. So using the given scaling symmetry, which will give us a similarity transformation given in the previous slide, we can convert the PDE, which is the heat equation. This is the ODE corresponding to the famous heat equation. If we take the heat equation to be UT is equal to UXX, then this equation is converted into ODE of this type by using the transformation eta, which is equal to x over under root t, x over under root t. So using this variable, this comes from the generator. That generator is the least symmetry generator, x partial by partial x plus 2t 2t partial by partial t. So this generator, we will use this generator in the characteristic equation to get this variable and convert this PDE into this similarity variable. We get this ODE. So this PDE goes into the ODE, and we promised in the beginning that a symmetry generator will give us a transformation which will reduce the PDE into ODE. Okay, wave equation and this generator. This is the generator, least symmetry generator of this wave equation, and this is the using the characteristic equation for it. This is the variable eta, and now let's convert this this PDE into ODE here. So you see, UT is equal to f dash, we use U is equal to f of eta, where eta is x minus t. Okay, so ut will be f dash, this is f dash, okay, f dash eta t. So that is f dash with a negative sign because eta t here is -1 and eta x is equal to 1. Okay, so again utt, so that give me again a minus sign over here, so this is plus sign and f double dash, that is utt. Now ux is equal to f dash, differentiating f with respect to eta and then eta with respect to x. You see eta x is 1, so this is f dash, and uxx is f double dash. Now let's put the values over here. This utt c square uxx, so utt is f double dash is equal to c square ux is also f double dash, so that implies 1 minus c square f double dash equal to 0. So I'm not taking 1 to be equal to c square, so that implies f double dash equal to 0. So this is now ODE because f depend only on one variable, which is eta. So okay, f double dash equal to 0, and we can easily integrate it. This will give me f is equal to c1 eta plus c2, where eta is x minus t plus c square. This is in fact u because u is equal to, so this is the solution corresponding to this generator, and it satisfies the given PDE. Okay, so PDE goes into this ODE. This is the corresponding ODE. Wave equation in a very simplified form. So this is the corresponding PDE-ODE. This is the corresponding ODE of the wave equation. So we did it. Substituting into the PDE gives ODE. The resulting solution represents a traveling wave solution. This one. And we did more general cases in the video of similarity and invariant solution. This is some part of that, but we did detailed calculation in that video. Here in this video we are only interested to tell about the reduction, how the reduction works in symmetry method. Okay, applications. In fluid mechanics, similarity transformation fluid mechanics. Okay, heat transfer, we see it in the example wave propagation. We also see it in quantum mechanics. We will have to do one separate video on this, that how the symmetry method work in the quantum mechanics. Our work is in space-time, in general relativity, where we use the Lie symmetry equation, and I think we did some Lie symmetries of space-time, of black hole space-time in some videos, so you can see that, and we will do some more videos on this topic using the approximate and other symmetries. Okay, if this is helpful, then like, comments, and subscribe. Thank you.